Have you ever looked up at the night sky and felt a sense of wonder? The universe is vast and mysterious. We see stars and planets, but could there be more? What if I told you that our universe might have more dimensions than we can see? Our senses tell us about the world around us. We experience 3 dimensions: length, width, and height. But what if there are hidden dimensions beyond our perception? These dimensions could hold the key to unlocking some of the biggest mysteries in physics and cosmology. Join me on a journey to explore the mind-bending world of higher dimensions. Let's start with the basics. What exactly is a dimension? Imagine a tightrope walker carefully balancing on a rope. The rope represents a single dimension, a line. The tightrope walker can only move forward or backward along that line. Now picture an ant crawling on a piece of paper. The ant experiences 2 dimensions, a flat surface. It can move left, right, forward, and backward. Finally, think about a bird soaring through the air. The bird experiences 3 dimensions: length, width, and height. It has complete freedom to move in any direction. These 3 dimensions define our everyday experience of space. But there's another dimension that's crucial to our understanding of the universe: time. We can't see or touch time, but we experience it constantly. Time flows forward, and it allows events to unfold. Just like the tightrope walker, the ant, and the bird, we are bound to move through time. Albert Einstein revolutionized our understanding of time with his theory of relativity. Einstein showed that space and time are interconnected. They form a 4-dimensional fabric called space-time. This fabric can be warped and curved by massive objects like stars and black holes. So we've explored the familiar 4 dimensions of space-time, but what if there are even more dimensions beyond these? That's where string theory comes in. String theory is a fascinating area of theoretical physics that attempts to unify all the forces of nature. At its core, string theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. These strings are incredibly small, far smaller than anything we can currently observe. String theory suggests that these strings vibrate in different ways, giving rise to the particles we observe and the forces that govern their interactions. Here's the catch: string theory requires the existence of extra dimensions to work mathematically. Section 5: Compactification: hiding dimensions in plain sight. Now you might be wondering, if there are extra dimensions, why haven't we seen them? It's a question that has puzzled scientists and laypeople alike for decades. String theory has an answer for that too: compactification. This concept is one of the most fascinating aspects of modern theoretical physics. Imagine a garden hose from afar. To the naked eye, it appears as a simple, one-dimensional line stretching across the garden. It looks like a one-dimensional line. This is because from a distance we can't perceive its true structure. But as you get closer, you see that it has a second dimension: its circumference. This hidden dimension becomes apparent only when you examine the hose up close. This second dimension is curled up and hidden from view at a distance. It's not visible until you change your perspective. Similarly, string theory suggests that extra dimensions are curled up or compactified at incredibly small scales, making them invisible to our current technology. These dimensions are so minuscule that even our most advanced instruments can't detect them. One extension of string theory, called M-theory, even proposes that there are 11 dimensions in total. This theory expands our understanding of the universe in ways we are only beginning to grasp. M-theory attempts to unify different versions of string theory, much like the theory of electromagnetism unified electricity and magnetism in the 19th century. Just as electromagnetism revolutionized our understanding of the physical world, M-theory has the potential to do the same for our understanding of the universe's fundamental structure. The idea of hidden dimensions isn't just a theoretical curiosity, it has profound implications for our understanding of reality. If these dimensions exist, they could explain some of the most perplexing mysteries in physics, such as the nature of dark matter and the unification of forces. The search for these hidden dimensions is ongoing. Scientists are using particle accelerators like the Large Hadron Collider to probe the fabric of the universe at the smallest scales. Each experiment brings us closer to uncovering the secrets of these elusive dimensions. As we continue to explore and understand these hidden dimensions, we may one day achieve a unified theory of everything, a single framework that explains all physical phenomena. This quest is one of the most exciting frontiers in modern science, promising to reshape our understanding of the cosmos. Section 6. Visualizing higher dimensions, the hypercube and beyond. Visualizing higher dimensions can be tricky, but we can use analogies to get a glimpse. By understanding lower dimensions, we can build up to higher ones. Let's start with a square, a simple flat shape that we are all familiar with. A square is a two-dimensional object. It has length and width but no depth. Now, imagine connecting each corner of the square with a new line, creating a cube. This process adds a new dimension. The cube is a three-dimensional object. It has length, width, and depth, making it more complex than a square. We can continue this process. By extending lines from each corner of the cube, we can create a new shape. If we connect each corner of the cube with a new line, we create a hypercube, also known as a tesseract. This is a four-dimensional object. The hypercube exists in 4 dimensions. It has length, width, depth, and an additional dimension that we can't directly perceive. While we can't fully visualize a 4-dimensional object, we can represent it mathematically and project it onto lower dimensions. These projections help us understand its structure. These projections give us intriguing glimpses into the geometry of higher dimensions. They allow us to explore concepts that are beyond our everyday experience, expanding our understanding of the universe. Section 7. The Large Hadron Collider, chasing shadows of extra dimensions. If these extra dimensions exist, how can we find evidence of them? One promising avenue is through particle accelerators like the Large Hadron Collider, or LHC. The LHC smashes protons together at incredibly high speeds, creating showers of new particles. Some physicists believe that if extra dimensions exist, they might be detectable in the way particles interact and decay after these collisions. For example, some theories predict that microscopic black holes could form at the LHC if extra dimensions exist. These black holes would be incredibly small and would evaporate almost instantly, but they could leave behind a distinctive signature in the LHC's detectors. Section 8. The implications of higher dimensions. A new perspective on reality. The existence of higher dimensions would have profound implications for our understanding of the universe. Imagine a world where the familiar 3 dimensions of space and 1 of time are just the beginning. Higher dimensions could fundamentally alter our perception of reality, opening up new possibilities and realms of existence. It could revolutionize our understanding of gravity. In our current understanding, gravity is a force that acts between masses, but in higher dimensions, it might behave in ways we can't yet fully comprehend. Einstein's theory of general relativity describes gravity as the curvature of space-time. This elegant theory has stood the test of time, explaining many cosmic phenomena with remarkable accuracy. But what if gravity is actually stronger than we think because it's leaking into these extra dimensions? This idea could provide a new perspective on why gravity appears so weak compared to other fundamental forces. This could explain why gravity is so much weaker than the other fundamental forces. In a higher dimensional framework, gravity might be diluted across these extra dimensions, making it seem weaker in our familiar 4-dimensional spacetime. Higher dimensions could also provide insights into the nature of dark matter and dark energy, 2 of the biggest mysteries in modern cosmology. These elusive components make up most of the universe's mass-energy content, yet we know so little about them. Philosophically, the concept of higher dimensions challenges our perception of reality. It forces us to rethink our place in the cosmos and consider the possibility that our senses are limited, only revealing a fraction of what truly exists. It suggests that there might be entire realms of existence beyond our limited senses. These hidden dimensions could harbor parallel universes, alternate realities, or even new forms of life, waiting to be discovered and understood. Section 9. The search continues, unveiling the secrets of the universe. The search for extra dimensions is a testament to human curiosity and our relentless pursuit of knowledge. While we don't have definitive proof of their existence yet, the journey itself is just as important as the destination. Every experiment, every theory, every observation brings us one step closer to unraveling the secrets of the universe. The universe is full of wonders, and the possibility of higher dimensions adds another layer of awe and excitement to our exploration of the cosmos. The quest for knowledge knows no bounds. Section 10. Further exploration resources for the curious mind. If you're intrigued by the idea of higher dimensions and want to delve deeper, there are many excellent resources available. Cosmos, A Space-Time Odyssey is a visually stunning TV series that explores a wide range of scientific concepts, including higher dimensions. The Elegant Universe by Brian Greene is an accessible book that provides a clear and engaging introduction to string theory and extra dimensions. Hyperspace by Michio Kaku explores the history of higher dimensions in physics and their potential implications. Remember, the universe is vast and full of mysteries waiting to be uncovered. Keep exploring, keep questioning, and never stop being curious about the world around us.